Welcome back to the Lowdown on Physics. This is screencast number 2 in a series on structures and materials, which is an elective in the Unit 3-4 Physics. So let's just do a quick review of the types of force that a material can experience. So firstly we've got compression, and that's where the force is compressing or pushing everything together, so the atoms are being squeezed together. Secondly, we have tension, and that's where the object's being stretched, so the atoms are being pulled apart. Thirdly, we had shear, and that's where we have parallel forces, but they're offset or they're not collinear, and the atoms are effectively sliding past each other. And finally, we had bending, and that's where we have a combination of both tension and compression. So today I want to have a look at factors, or what stress is, and the effects of stress. So factors, or what's stress firstly? Stress is basically what happens when a material is experiencing a force. Factors that obviously will affect that then are force, but also the size of the material. So particularly we're looking at the cross-sectional area of the material. So if we consider two rubber bands, different cross-sectional areas, so different width for each elastic band, they both got the same length initially. If we subject them to a weight, what we would expect is that we'd have greater stretch caused on the one with smaller cross-sectional area, assuming it's made out of the same elastic material, of course. So let's define this mathematically. So stress is the applied force per cross-sectional area. Remember to use your SI units. So mathematically, we've got stress equals force over area, or if we want to put that in symbols, we use the symbol sigma for stress is equal to F over A. So we've got units of newtons over meters squared. So the SI unit would be, just a quick warning, units would be newtons per meter squared, but that's also equivalent to the Pascal. So 1 newton per meter squared is equivalent to 1 Pascal. So let's just quickly work through a basic example applying the stress equation. So we've got an experiment, we've got various weights that have been hung on the end of a bit of copper wire. The diameter of the copper wire was 0.5 millimeters. Which sounds, it's a thin bit of copper wire. So work out the cross-sectional area of the wire. So area for a circular area, assuming that wire is circular, is pi r squared. So substituting in, we've got pi times 0.25. Okay, remember that's the diameter. So there's the first trick, is to watch for diameter, and they will do that a lot. Halve the diameter, then we need to put it into meters. So millimeters to meters is multiplied by 10 to the negative 3, or divide by 1,000, and then square that. So what we'll find is we end up with a very small cross-sectional area. So that's 1.963 times 10 to the negative 7, and units would be meters squared. So now calculate the tensile stress. So putting 3.5 kilograms onto that, the formula was sigma equals F over A. So we've got 35 newtons, got to convert that to newtons. So multiply that by 10 to get 35, divided by the cross-sectional area that we just calculated. When we do that, substitute in, we get 1.78 times 10 to the 8 pascals, or 178 megapascals. So mega means 10 to the 6, so that means we move that twice to make it 10 to the 6. So we get 178 megapascals. Unless it asked for that in its units, you don't need to convert it to that. That's a very reasonable stress, so you will end up with big numbers when you're calculating stresses or high stress. Finally, what would the size of the stress be if 1 mm wire was used? So we've got sigma equals F over A. So substituting in, 35 over pi r squared, so we've now halved r. We get 0.5 times 10 to the negative 3 squared, and we end up with 4.456 times 10 to the 7, or 44.5 megapascals. If you remember, the last one was 178. This is 1/4 of the original what do you call it? Stress. Sorry, mind blank. That's 1/4 of the original stress that we had. So doubling the radius gives you 1/4 of the stress. That's because we square the radius. Okay, so lock that in your memory bank. Double the radius, 1/4 of the stress. So I just want to introduce another term now, and that is the term strength. And basically it's the maximum stress before failure. Failure is where it's going to break. So strength is maximum stress before it breaks. So the breaking point. So it can occur under compression or it can occur under tension. So tensile strength, maximum strength before it fails under tension. Compressive strength, maximum strength before it fails under compression. So just a bit of a Kodak moment. This is really hard to tell what it was. This was originally a radio telescope, so a big dish. It was in the US, and they had little tiny cracks developing near some of the bolt holes, and basically that just led to maximum failure. So yeah, destroyed. Okay, just a couple of examples here of a few common materials and recorded compressive strengths and tensile strengths. So cast iron, great under compression, good under tension but nowhere near as good. Steel, very good under tension and also quite good under compression. Brass, same either way. Carbon fibre doesn't cope with compression but very, very strong under tension. Granite, the complete reverse, great under compression, not tension. And concrete, great under compression but struggles with tension. That's why we reinforce concrete, but we'll get to that in a minute. So when we're designing a structure, these sort of calculations are invaluable, but really they're only a guide, because this is sort of ideal conditions, and when we actually build a structure, there's certainly going to be imperfections in the structure, maybe little microscopic cracks or impurities in the material as they construct that material. So we use these as a guide. So to help in the design process, we have something that we call a safety factor. And the safety factor, the purpose of the safety factor is to account for these weaknesses in the materials. And generally they would vary from maybe 4 to about 10. So if we had a safety factor of 5, it would mean that we want to use 1/5, or the maximum stress should be 1/5 of the strength, 1/5 of its breaking point. So if its breaking point is 80 megapascals, then you'd want to use, and a safety factor 5, you'd use 1/5 of that, which would be a maximum stress of 16 megapascals, say. So just a quick example here, we've got a marble column with a diameter of 20 centimeters. There's that diameter again, so we need to halve that when we're finding area. We're told maximum compressive strength is 10. We have a safety factor of 80, a safety factor of 10. What's the maximum mass that it can take? So taking that information, of course, ordinarily we'd list all of our variables before starting our equation. We've got sigma equals F on A. Now, sigma maximum stress, or the strength, was 80 times 10 to the 6. We want to allow for a safety factor of 10, so we're dividing by 10 to get our maximum stress that we want it to experience. That equals F over the area, pi times 0.1 squared, because it was 20 centimeters. We want 10 centimeters, and then putting that into meters. That gives us a force, when we rearrange, equal to 80 times 10 to the 5 multiplied by the cross-sectional area. Maximum force it can have is 2.5 times 10 to the 5 newtons. Divide by 10 to answer the question. It asks for maximum mass, 2.5 times 10 to the 4 kilograms. I mentioned reinforced concrete a moment ago, and that's a good example of a composite material. And a composite material consists of 2 or more materials but they must retain the properties of their ingredients that you're adding. So examples would be things like reinforced concrete or fiberglass or mud bricks. And so, you know, as with the example of reinforced concrete, we've got concrete great in compression but really poor in tension. So we put steel in the places where it's going to experience tension to strengthen it, and therefore we get good tension and compressive properties for the material. So looking at a typical exam question, we need to look at where would we put reinforcement in this steel slab, and then they'll usually give you multiple choice questions, so you get 4 options of where you'd best do it. So think about the structure itself. Concrete's great under compression, so it won't need reinforcement where there's compression, but it's really weak under tension. So if we think about it, in the center of this slab, it's going to sag under the weight. Center of mass would be somewhere here, so there'll be a little bit of sag in the center. So without putting support there, we're going to get cracking there. Also on this side, it's going to sag and bend over the end. So we're going to have compression here, that's fine, but we'd have tension at the top. So we'd start to get cracks appearing at the top. So we insert the steel rods in positions to prevent any cracking occurring where the compression is. You know, you're guaranteed a question like this almost certainly on your exam. So you'd want at the bottom here steel rods, and then at the top over here steel rods. And there's 2 marks for one of your multiple choice questions. Alright, good luck, and I'll see you in class shortly.